This is TWiT.
If you would just kind of give us a run up for people who may not have been exposed to this, what is space solar power and its key advantages?
So in space near Earth, the sun shines 24/7 and has about 30% more energy in a square foot of or a square meter of sunlight than the brightest, clearest summer day in Arizona here in the U.S. So about 1,400 watts per square meter in terms of energy versus about 1,000 watts per square meter at midday on a clear day in the desert near the equator here on Earth. Space solar power is the idea of sending large systems, building them up in space, build them in space, and use them to harvest the solar energy, which is more intense and constant there, and send it by wireless means to markets here on Earth. Very simple concept. And as I mentioned, it's been around since the late 1960s as an operational idea, and for 80 plus years as a vision in science fiction.
Can I ask, I mean, John, it is a simple concept, it seems. You know, you're thinking about renewable energy, you think about solar panels, you put them where the sun is always shining, and then you beam that to Earth. It seems like so beneficial the way that you describe it, and yet here it is 2024, and we still don't have this stuff. I mean, I assume that there's either some sort of insurmountable technical hurdle or something for a reason that we haven't done it, or what is there even one overarching thing that we don't have it if it's been studied since the 60s?
So fundamentally, the physics of a solar power satellite is extraordinarily well established. It's the same physics, the same component engineering that is used in every communication satellite that ever flew, Starlinks to TDRS up in tracking and data relay satellites up in geostationary Earth orbit. Same physics that makes GPS a success, which we use every day for everything to get to anywhere in our cars. The issue with space solar power, with the concept of the solar power satellite, it's not the physics, it's not the basic technology. It's not like, for example, with fusion, where after 70 years of research, they're still just inching up on break even after tens of billions of dollars. So the physics is not yet proven for magnetic confinement fusion, as an example. Just the last year or so, laser detonation fusion was proven here in California at the UC system. But the problem is cost. Mm-hmm. Solar energy, thank God, is fairly diffuse. Otherwise, we would all fry. Yes. But that means that systems that are going to collect solar energy and deliver it in meaningful scale to the markets on the Earth have to be huge. Mm-hmm. And the challenge when these things were looked at first in the 1970s was that even though they were technically feasible, no one's ever argued since 30 years ago that it wasn't technically feasible. The issue has always been economics. And as I'm sure we'll get into in a few moments, it's these barriers, the economic barriers, that have started to fall in the last decade.
And I guess I know you kind of touched on it, but the hardware that we're talking about is, you know, you've got a satellite, we've got that technology set, but is it the receiving end then, the costs for that and setting that up, and then I guess you have to get all of the permissions, you know, to build anything like that, and work with people who maybe don't want power being beamed down from space in their backyard. Is that the cost that we're looking at right now, or are there advances that we have to make to get that efficiency to where it's economically feasible?
So you absolutely have to improve the efficiency of the key technologies, photovoltaic cells, wireless power transmission, the cost of launch, all of those things. Improvements are needed. However, the engineering of wireless power transmission was first demonstrated on the Walter Cronkite NewsHour in 1963. So so it's got a long heritage. The problem is how to do it not on a kilowatt scale, like a microwave oven kind of scale, but to do it on 1,000 megawatt scale, which is sort of at the scale at which you're powering cities. And those are remarkably large systems.
Mm-hmm.
And in those cases, it's not. And I give you one example of how the technology has changed. So in the 1970s, when this was looked at, photovoltaic cells were still relatively new. Nobody was using them on Earth. And for space, the estimated efficiency was 10%. So 10% of the sunlight falling on a photovoltaic cell in a communication satellite, 10% of that sunlight was turned into electricity. Today, the efficiency for operational cells, PV cells, for example, for satellites, is up to 30%.
Oh, wow.
So threefold improvement. And that directly reduces the amount of area of PV cells that are necessary for a given amount of power. And in the laboratory, efficiencies up to about 50% have been achieved. So there's huge improvement since the 70s, room for more improvement. Similarly, do you mind if I just give a couple more?
Yes, please.
Okay. So similarly, in the cost of launch, so it has always been said, oh, space is hard. It's always going to be expensive to go to space. You know, it costs $30,000 a kilogram or $10,000 or $20,000 a pound for the space shuttle to launch anything to space. And that's just the way it's got to be.
Mm-hmm.
And that's what people believed right up until 2015. When the first Falcon 9 reusable launched.
That's right.
And before that, it was an article of faith among good, solid, conservative, reliable systems engineers that in radically improving the cost of launch was a bridge too far. It was just not something we were going to be able to do. And now all of a sudden, 9 years ago, this thing is going up and coming down and going up and coming down. And it's not just that it's reusable, but the booster itself is cheap.
Yeah.
And so today there's SpaceX is working aggressively on the Starship with its big booster and is anticipating costs will go from around $2,000 a kilogram where they are with the Falcon 9 reusable down to around $200 a kilogram. And that's down from $20,000 with the shuttle or $35,000, $40,000 a kilogram, depending on how you rack and stack the costs with the SLS launcher. Reusability is key, and suddenly everybody knows it can be done. There's reusable launcher programs in China, in Europe. Here in the U.S., there's also Blue Origin. There are innovative ideas to go beyond rockets, like space elevators and spin launch. And so all of a sudden, in just the last dozen years, less than 10 years, the cost of launch as a barrier to big visions in space, like space solar power, has plummeted by one order of magnitude so far, and the cost is projected to plummet by at least another order of magnitude, or maybe only a factor of 5 during the next half dozen years.
Wow.
Lastly, the other big component in these very large systems is the cost of the hardware. So you got to be able to collect, convert, and transmit the energy efficiently. Talked about that. You got to be able to get these big systems into space at an affordable price. Talked about that. The last one is how much does the platform itself cost? Because it's going to be huge. Mm-hmm. And in the last 5 years, it has been proven by Starlink, by OneWeb, by Kuiper System, by all these programs that are commercial programs that are pursuing mass-produced space hardware, that you can make space systems super cheap for on the order of $1,000 a kilogram or less. Whereas traditionally, a large satellite and geostation in Earth orbit was projected to cost on the order of $100,000 a kilogram. So there again, this is one where it's already proven that if you can make your system like Starlink or OneWeb or Kuiper, if you can make your system out of lots of small pieces, and you can mass produce those pieces, even though they're complicated space systems, just like jet engines, just like the avionics in an Airbus 350 or a Boeing 777, and do it at a very affordable price. So with those three barriers being shattered really, over the last 10 years, it radically changes the doability and the economics that you can expect for space solar power.
Hey, if you enjoyed this clip, be sure to check out This Week in Space. You can find us on your favorite podcast app or see the link in the description below. See you there.